Good morning, or almost afternoon at this point. We are Skywave Innovations. I'm Amanda Schlarman, Julian Gonzalez, and my team members, are Julian Gonzalez, Bill Perskenis, Zhang Zhen, and Brandon Weiser and Wayne Hendricks. We are, Collins Aerospace tasked us with designing a low-profile, long-range HF antenna that will replace the long wire on the Boeing aircraft system. Now, while the current design is simple and effective, it spans most of the aircraft. So our task is to shrink that down and make it to lower profile while maintaining the characteristics of the long wire, which will be a difficult task.
Using ANSYS HFSS, we modeled and simulated shunt, inverted V, and hybrid antenna designs. Currently, we're pursuing the shunt antenna design due to its low profile, simplicity, and gain plot. If you look to the top left of the screen, you can see the placement of the original long wire design. Below it is the shunt and the proposed location of our shunt antenna design. We were unable to gain access to hardware that was able to run our simulations until later on in the semester. Therefore, the radiation pattern and gain plot you see here are of our initial design.
Our next step is to model the different variations of antennas that we have. We plan on modifying each antenna to improve the gain, to improve the radiation. To do this, we have a trade study which has different measurements, scalability, and we will then choose our antenna based upon that. And once we choose that antenna, we will then go to the next phase, which is construction.
So based on different aspects of materials of study, such as conductivity, resistance of oxidations, and the price. So we are choosing aluminum as our main material for our prototype building, which is the most commonly used material for HF antenna design. And then we are planning to scale it down 4.9 times in order to make our construction realistic and make the frequency falls into our testing range.
And so that we can test our actual antenna, and we're going to be focusing on 142 megahertz. One, because that is the hand radio that we're going to be using only receives high frequencies. So the filter that I designed focuses on 142 megahertz. It is a five-stage pi-type filter. It has about a 600K 3 dB bandwidth.
And I'll be validating the results we get from ANSYS. I'll be putting the scale models we make into a wide open area and taking measurements from around it with an oscilloscope, while broadcasting a constant waveform on the antenna, and then compare those results to what we would expect from ANSYS. I will also be putting the models through a wind tunnel so we can compare the low profile of each antenna. Are there any questions?
What gain are you expecting to get from the antenna in dBi?
I do not know dBi, but I know that the transmitting power we'll see an increase of about 3 to 4 dB in gain.
So you're trying to improve an existing antenna by a factor of 2.
We're trying to match the existing antenna as best we can. The existing antenna has a power gain of about 3 to 4 dB.
dBi, you mean?
Yes, sorry, dBi.
Okay, so you're trying to match that. You're not trying to improve it by another 3 dB.
No,
You mean double it.
No.
Okay, while maintaining size or reducing size?
We're trying to reduce the size and achieve a lower profile with our new antenna design.
That's a challenge, right? The
Yeah.
size, I mean, the gain is usually derived directly from the size.
Mm-hmm. And coming from a long wire to a smaller profile is definitely a challenge that we were facing.
And why is there a filter needed in this whole?
Well, on the prototype that we're going to be building, in order for us to test it, and also size restrictions as well, we need to be able to filter out all the noise so that we can better test our antenna.
If you're going to be testing it with some high power level, then whatever unwanted noise may be way down there and not in your way. Just finding it hard to understand why you need a filter to characterize or design an antenna.
Oh, and
What-
reducing interference with other antennas on the aircraft.
Oh, okay, so the filter is needed apart from the antenna in the actual target application.
Yeah,
So
so
it's
it's
not
not
part
stepping
of
on the others, yeah.
the environment for the design of the antenna, but it's just a need.
Yeah, okay, that's correct.
Okay, so that wasn't made clear. And how can you do your experiments and development at 142 megahertz and then use that for a different band entirely? I mean, there's a very big difference between 2 to 30 megahertz and 140. 142 megahertz is a 2-meter wavelength, right?
Yeah.
And then this is much greater of a wavelength.
So one of the reasons why we had to pick a higher frequency is because of size restrictions. That's
Oh,
one
okay,
reason.
so the whole
It
project
can still
and-
be scaled.
Okay, so you will be delivering an antenna in VHF rather than HF. And hopefully, based on this experience, you'll be learning something that could be applied in HF.
Mhm.
But you're not doing circuitry in 142 megahertz and expecting to deliver an antenna in the desired band, right?
Right. That's
Okay.
All right, let's thank the